So this is like one simple example. So you have CNN fully connected, so you'll have to flatten it, and finally you are getting, let's say, 4 different values. So what is happening at this point, you will have to flatten this volume. So you will have a feature vector which has 5 cross 5 cross 16 different values, which will be connected to 400 different neurons. Now, to convert this to a fully convolution network, what you can do is, so this part is not going to change. You can still apply like a 5 cross 5 kernel on this. And if you do that, then you will be only able to apply that kernel once at the center of this, right? Because the resolution is 5 cross 5. And then you will use 400 such kernels to get 400 different values. And then you can have 1 cross 1 kernel. Again, if we give you something like this, and again, you can have like 4 different kernels, which will provide you like 4 different values, which you can use as prediction. So both are doing classification, and both have almost similar structure. The only difference is, in this case, you are using fully connected layers at the end, and in this case, you don't have fully connected layers. It's completely convolutional. Okay, so let's talk about the use case of this. Now, convolution, you know that once you have learned this model, then it doesn't matter like what is the input size of your image. Okay, and again, think about this. So in this case, it's 14 cross 14 cross 3. Now, what will happen if instead of 14 cross 14 cross 3, I use a much bigger image? Let's say 28 cross 28 cross 3. Whatever model or network you have trained, you will still be able to use that. And the reason is, whatever kernels you have 5 cross 5 over here, you will still be able to apply those kernels on the input image. It's just you will apply at more locations. And that's only going to change like the shape of this feature volume here. It might go to like, instead of 10 cross 10, it might go to maybe 25 cross 25 or 26 cross 26, right? And still you will be able to perform this max pooling operation. The only thing is going to happen is the spatial resolution will change. It might not be 1 cross 1. It might be, let's say, 4 cross 4 or 6 cross 6. And still the same weights, same network will work. And at the end, what is going to happen is, instead of getting like 1 cross 1 cross 4, you will get like some spatial resolution as well. It's a 4 cross 4 cross 4. And it's up to you how you want to use that. You can either just do average pooling of that. And again, you can get your 4 predictions if you want to use like this kind of architecture for classification. So what it's doing is, during test time, let's say if you have a bigger image, even without resizing, you will be able to do this network on that bigger image and be able to make predictions. Okay, so that's one use case. Now, the more interesting use case for this fully connected network is, if you think about like the programming assignment you have, the third programming assignment, where we're asking you to build an autoencoder. Now, in that case, if you don't have fully connected layers in between in the bottleneck, you just keep it fully convolutional. So you will see that if you train your autoencoder network, which is fully convolutional, in let's say a very small resolution image 28 cross 28, you will still be able to use the same network on an image which is, let's say, 500 cross 500, right? And still, like, let's say if you're doing autoencoding, you will be able to do autoencoding on the bigger image as well. If you are doing colorization, you will be able to colorize the bigger image as well. Okay, so that's, I think, a very interesting use case, and that's autoencoder is one example. But I think where it's applicable, if you try to bring all those problems under a single umbrella, you can say it's kind of a dense prediction task. And later in the course, we will look into some of those problems. So one of the dense prediction tasks is, let's say, image segmentation, where given an image, for each pixel, if you need some kind of prediction. Okay, so that you can say is a dense prediction task. And in that case, if you use like a fully convolutional network, then you can change the resolution of your images no matter what, but still you will be able to use the same network to make predictions on that varying like images with varying resolution. Okay, so that's a very, very interesting use case of this. But of course, you can use it for classification as well as we discussed.